So molecular compounds have nonmetals, and they're bound together by sharing electrons with each other. Because they don't have charges, we cannot use charges to predict how many there are of each atom. The other thing that's kind of makes things a little more complicated is between the same two elements there can be multiple compounds. We've already looked at water, H2O, and hydrogen peroxide. Right? Both hydrogen and oxygen, just different numbers of each. Between nitrogen and oxygen, you can actually get 6 unique molecular compounds. So we can't call that nitrogen oxide or something like that, because which one do we mean, right? So we're going to use the numerical prefixes. Now, these are the same prefixes we just looked at for the hydrates. The thing about this is students like the numerical prefixes and they want to use it for everything. Aside from the hydrates, you should not be using these prefixes for ionic compounds. It's so tempting, but don't do it. Only when you have 2 nonmetals. There are other molecular compounds that contain more than 2 nonmetals, but we're not going to learn how to name those. We're just going to stick to these binary molecular compounds. So we just use a numerical prefix before each element's name to say how many of that element there are. We usually put the more metal-like element first. Usually that's going to be the element with the smallest group number. So I'm telling you this, you're actually not going to probably have to remember that, because usually you're given the element name, the compound name or its formula, and it's already in the correct order. But there's that stair-step line, and so if you're trying to decide which nonmetal to go first, whichever one is closest to the stair-step line is going to be with the one that's more metallic, and that's the one that goes first. So here's the basic structure for binary molecular compound names. A prefix in front of the first element, a prefix in front of the second element, and then we change the ending of that element's name to "ide," because they are getting together here, so it's a little bit like marriage, as much like marriage as ionic compounds are like marriage, right? But it changes the ending of the name. The one exception to this prefix business is the prefix mono. Mono means one, and like we've been dropping ones all over the place, we often drop the mono in front of the first element. So we look at this NO2, and following this strict pattern, we'd say mononitrogen dioxide. But we drop the mono in front of nitrogen. We just call it nitrogen dioxide. Okay, because if it was some other number of nitrogen, there'd be a different prefix there. There are 2 compounds that always use their common names. Okay, this is like, Cher or Prince, or the artist formerly known as Prince, but that's not a single word anymore. So instead of calling this dihydrogen monoxide, which, is fun to scare your friends with, my teacher made us drink dihydrogen monoxide today, I'm going to die. And we drank water because we were thirsty. H2O, we always call that water. Okay? And we usually don't have trouble with that one. NH3, the systematic name would be nitrogen trihydride, but we don't call it that. It's always called ammonia. Okay? And I might try to trick you with that on an exam. Okay? NH3 is ammonia. So let's name this compound N2O5. So how many of the first element do we have? 2. So we're going to use a prefix di in front of that element's name. So di, nitrogen. How many oxygens? 5. What's the prefix for 5? Penta. So penta. And then we're going to take the name oxygen and change it to oxide. Pentaoxide. We will see that sometimes the ending vowel on the prefix gets dropped in front of a name like oxygen that starts with a vowel. Sometimes it isn't. I will not try to trick you on that one. because for some of them I've seen it both ways, and so it is confusing. So if you see a missing vowel, just say, oh, it's one of those things. Any questions about that one? And then we should be able to write formulas. So phosphorus tribromide. Well, the symbol for phosphorus is P. The absence of a prefix tells us there's only one, and so we're not going to write a subscript either. Tribromide means 3 bromines. So I put the symbol and the number of it after as a subscript. Yes?
As a rule, phosphorus forms a negative 3 ion, bromide forms a negative 1. How does
Yes.
that get together?
That's an excellent question. So phosphorus, we've learned, forms a negative 3 ion. Bromine forms a negative 1 ion. How can they bond together? That is why this is not an ionic compound. Because if these were ions, they would repel each other, right? But phosphorus atoms and bromine atoms can get together and share electrons. Okay, so this is a covalent compound. They're sharing the electrons. There are no charges to help us understand how many of each element, and so we need the prefixes. We do not use the prefixes for ionic compounds because they are not needed. Excellent question. Anybody else? And then there are the acids. So acids can be defined, that's the word. Acids can be defined a couple of different ways. This is what we're going to work with now. Acids are molecular compounds that release hydrogen ions when dissolved in water. So an acid is a molecular compound. It's formed of nonmetals. But when you dissolve it in water, it becomes ionized. Okay? So acids in this class are always going to start with hydrogen, and then there will be one or more nonmetals that come after the hydrogen. So an example here is HCl. Pure HCl is a gas and would be named hydrogen monochloride or hydrogen chloride. When we dissolve that in water, though, it ionizes, and it forms hydrogen ions and chloride ions. And when we put this AQ after a formula, whether it's an ion, an atom, or a molecule, it means dissolved in water, aqueous. So it forms hydrogen ions and chloride ions. If you have a compound that it might have H, hydrogen, and another nonmetal in it, but if it won't dissolve in water, then it's not considered an acid under this definition. Acids taste sour. They dissolve many metals, and their formulas start with H. Here's an example. Zinc metal will react with an HCl solution, and the metal will dissolve. There will be a lot of bubbling of hydrogen gas, and then at the end, the metal's gone. So some metals, not all metals, can be dissolved in acids. So when we're naming acids, there's two different types of acids. Your book talks about binary acids containing only 2 elements. Don't really like that definition because there's a couple exceptions. And then oxyacids are acids that contain oxygen. I prefer to think of them as oxyacids and the other kind. Oxyacids always have oxygen. They start with hydrogen, and then they've got an oxyanion, like chlorate or sulfate or something. And they're named differently. So we'll look at the binary acids. Here we're going to use the prefix hydro. These acids are mostly going to have hydrogen and one other nonmetal. So we use the prefix hydro to indicate the hydrogen. We take the base name of that nonmetal, we change its ending to ic, and then we throw the word in acid after there. So an example would be this. So HF aqueous. The aqueous tells us we need to name this as an acid. It starts with H. We need to name it as an acid. There are 2 elements here, hydrogen and fluorine, and so we use the prefix hydro. And fluorine we change to fluoric. So hydrofluoric, and then the word acid. So these are also going to have two names. It's just the second name is acid. Questions? Then there's the oxyacids. The names of the oxyacids are based on the name of the oxyanion that's present in them. So if your oxyanion ends in 8, we're going to change the ending to ic and add the word acid. We don't use any hydro at the front. We're just going to take the oxyanion's name, change the ending, and put the word acid. If the oxyanion ends in ite, you're going to change the ending to us and add the word acid. Okay, that can be a little difficult to remember. Ite, ate, ic, and us. So there's a couple silly sentences for that. They're not technically mnemonics, but the one I've always used is, Rick ate him before he could bite us. It sounds a bit barbaric. Rick ate him before he could bite us. Okay, so how does that help? Here we have ick and ate, ite and us. Another one that I've seen a lot is the white mouse ate icky cheese. So the white mouse ate icky cheese. And again, that gives us a way to tie those pairs together. Here we have ite and us, ick and ate. So you got to figure out a way to remember that. So name the acid. HNO2 aqueous. It starts with H. It's got aqueous. We name it as an acid. We look at this and we see there's hydrogen, nitrogen, and oxygen. This is an oxyacid. And so what we're going to do is we're going to cover up the H and ask ourselves, what is the name of that anion? That's nitrite. Nitrate is NO3. This is nitrite. Right? So we identify the oxyanion is nitrite. And so we need to change this ending. Ite changes to what? Us. So this becomes nitrous acid. Any questions? You don't put hydro. We only put hydro if it's a binary acid. There's no oxygen. Then you use hydro and whatever the element name is. But these are named based on the name of the oxyanion, and we just change the ending and put the word acid. The number of hydrogens in this formula is directly related to the charge. Right? So nitrite has a charge of 1-. Hydrogen ions, this is one of the reasons that hydrogen is often over there with the alkali metals on the periodic table. Hydrogen forms a +1 ion. So we need 1 hydrogen to balance the charge on nitrite, or nitrate. If you had sulfate with a 2- charge, you'd need 2 hydrogens because they have to be neutral. So these are molecular compounds, but they form ions when you put them in water. Let's write the formula for perchloric acid. Well, ic goes with which suffix? Ate. So this is from perchlorate. So this has perchlorate ion in it. So we're going to write the formula for perchlorate, ClO4-. We have to add hydrogens onto that to make a neutral compound. Because this charge is -1, we only need 1 hydrogen. And so perchloric acid is HClO4. That's a kind of messy 4. And it's aqueous. Any questions? Yeah.
So when it comes to acid, it always has a hydrogen?
Yes, in this class, acids will always start with hydrogen. Any other questions? This is something that needs some practice, and that's why I put up those extra assignments, and they are extra credit on, that'll give you some extra practice on the naming of these different things.
Are those in master and chemistry?
They're in master and chemistry, yeah. Writing the formulas, we just did one of those. Whenever you see the name, these are really easy to recognize, right? Because they have the word acid in their name. So yeah, they're acids, right? If it ends in acid, it starts with H. So you write the formula as if it were ionic, even though we know it's a molecular compound. But we know that when we put it in water, it forms ions. And so the charges of the ions tell us how many H's we need. So the hydro prefix means it's a binary acid. No prefix means it's an oxyacid. For the oxyacid, we name it based on the polyatomic ion. So let's write some formulas, okay? So hydrocyanic acid. What does this prefix hydro tell me? It's a binary acid. So there's no oxygen involved here. So cyanic, what's that? It's from cyanide. Cyanide is not an element. How can this be a binary? That's why I don't like it. They call this binary. Well, so cyanide. Cyanide is Cn minus. It is not an oxyanion. It's one of the other kind that the book calls binary. So we need to add hydrogen to that so that the charges add up to 0. And so the formula for hydrocyanic acid is HCN aqueous. It falls into that category of binary acids even though it's got 3 nonmetals. Any questions? How about phosphoric acid? There's no hydro at the beginning of the name. What does that tell us? It's an oxyacid. Okay? So phosphoric, what do we change that ending to? 8. Rick ate him. The white mouse ate icky cheese. So this is phosphate. So we need the formula for that. We should have that memorized. PO4, 3 minus. And we're going to add hydrogen ions. And so the charge, the negative charge on this tells us how many hydrogens we need. We need 3 of them. So this is H3, PO4, aqueous. And I won't try to trick you with the aqueous business either. I'm just trying to be consistent. Questions? One more. Hypochlorous acid. Now this prefix hypo is similar to hydro, but it's not the same, is it? So here we have no hydro in front. That means this is an oxyacid. So we're going to look at hypochlorous and change the us ending to what? Ite. So this is from hypochlorite. Oh, I've got an extra I in there. Hypochlorite. So chlorate is ClO3. Chlorite is ClO2. Hypochlorite is ClO. It's got a -1 charge. And we need to put hydrogen ion with it. It's a -1 charge. We only need 1 hydrogen. So the formula is HClO aqueous. Questions?
Does hypo just take away?
Hypo just means 1 less oxygen than chlorite. Yeah. I'm going to skip that.